Thank you, everybody. I'm so grateful to be here, and thank you, Jeff, for the kind introduction. So, when you're looking at disaster resilience, one thing we need to know is that the world as we see is rapidly changing. The number of disasters we're seeing on a yearly basis, we're seeing impacts we've never seen before. There's a lot of uncertainty, even quantifying the disaster impact risk. And this is exacerbated with things like climate change. It's exacerbated by things like globalization, wherein no longer are businesses, communities, or citizens independent when you think about their daily functionality. There's high amount of interconnectedness. And when you want to actually describe is if a particular organization is affected, you need to look at the uncertainties happening because of the real-time events because of climate change, as well as the uncertainty caused by the cascading impact analysis across the network. An example would be, say we have a hospital. The hospital itself, first of all, how do we predict whether or not the impact to that hospital is as accurate as possible? And the second thing is that even if the hospital is ultimately up, is it actually functional? And in order to understand that functional aspect, we need to look at other things beyond the hospital, like does it have water, does it have power, does it have transit, etc. So these two problems exacerbate just the fundamental problem of predicting disaster impact analysis. And that's wherein we see there's a big gap. When we think about holistic disaster resilience, it's number one, making sure that we're predicting the right disaster impact and it is validated against the recent events we're seeing. And number two is also talking about how do we then actually predict the business functionality loss and not just about the structural functionality loss. Now, and that's what exactly we're trying to do at One Concern. So our mission is to help, is to use artificial intelligence techniques and physical models and different non-traditional techniques to really predict what the disaster impact could be, both before a disaster as well as after disaster. And we see a world wherein ultimately there is holistic resilience, wherein businesses and communities understand both this direct and indirect impact. What does this use case actually mean? So during a disaster or post-disaster, it's unfortunate that right now we can't even answer the simple questions. The simple questions of which buildings have been impacted, the question of who should we rescue, the question of who should we evacuate. All these questions are unanswerable right now, and that's pretty unfortunate, right? You would assume that in an age wherein you have artificial intelligence techniques to predict like what you're going to buy 3 months from now, this question, which is a fundamental question related to life safety, is being worked upon. And that's one of the key components of focus which we at One Concern focus on. The second part is in the pre-disaster analysis piece, which is if the disaster impact is incorrect or it's hard to quantify, how are we actually making policy decisions right now, either in cities or through insurance? How do we actually know what true risk is? So there's a lot of uncertainty in that as well. And we aim to try to get data-driven policy decisions by working with our stakeholders. Today, I'm just going to talk about the difficulties in taking these algorithms to market. How do we try to be better than just plain traditional physical models? Number one is that when you're thinking about your machine learning algorithm, or when you're thinking about just the algorithms in themselves, you have to make sure that the algorithm is tied to the business use case. Right? The underlying physical process or the underlying model itself is the same problem statement for either a city or a business or insurance, which is what is the impact to a particular building. But your machine learning KPIs can be drastically different. And what do I mean by that? So if you're a first responder, so you're a police or you're a fire truck, what you actually care about is how many buildings are damaged or in the highest damage probability immediately after an event. You're okay with getting the error in the low damage states, but you want to make sure that the high damage states are as accurate as possible. And so you want to make sure that your machine learning algorithm or the ultimate algorithm is tuned to be solving that particular use case. Now, if you look at another type of organization, say Red Cross. Red Cross comes in after the disaster has happened. And one of the main tasks they focused on is setting up shelters. Now, do these people care about where the most damaged buildings are? Yes, of course. But they want to know where to set up these shelters. And these shelters typically should be focused on low damage locations surrounded by clusters of high damage. So that's what you want your KPI to be focused on. And again, the problem statement is similar, but your KPI should be tied to the business objective. And the third one I want to talk about is just financial institutions, maybe say insurance. So insurance comes in when a disaster happens, and it's important to very quickly provide the claim and provide the right claim. Now, obviously, as everybody understands here, while you're doing claim assessment, you're sending people on the ground to figure out exactly what sort of damage did you observe in the earthquake. Now, you could argue that, should we be equally accurate across the low, medium, and high damage? Now, low damage, the probability of getting a claim might be very low. So maybe you don't want to send somebody there first. High damage, you probably already have a good estimate that is definitely going to be collapse. So maybe that's not where you want to focus first. You want to focus on the places wherein there's highest uncertainty among whether or not this particular building is damaged. And that is sort of what your KPI should be tuned to. When you are trying to solve the answer of where should I send my claims assessment officers and how do I get that information so my algorithm becomes better over time and I can reduce the total time taken to actually predict all of this. So notice for all the three different use cases I talked about, the underlying model is still the same, but your machine learning KPI is very, very different. And you need to understand that this KPI can only be understood when you talk to your customers. And if your KPI is incorrect, ultimately it doesn't matter whether you know how accurate your model is. The second thing I want to talk about is disasters are pretty extreme events. So there are a lot of things which can change over time. And ultimately, a model may not be able to predict those, right? You have, in a flood, you might have the river course change, a dam may explode, a tree might fall into the river. So even if you model the impact, how are you going to model the changes because of these particular sort of events? It's highly difficult to do that. So what we need to do is that once we do have algorithms in place, how do you look at real-time observations to automatically update and calibrate the model, as well as how do we leverage existing experts, existing emergency managers, or existing claims assessment officers who can verify whether your algorithms are doing right based on historical observations. So, and this should be done both in a pre-disaster and a post-disaster impact stage. In a pre-disaster impact stage, what we try to do is before we deploy to a city, we run all the historical simulations using our algorithms, assuming that it has never seen the event before, and we present this to the user who's actually using it. Sometimes they help us know that, hey, actually, this location is a little bit inaccurate, and I think it's because you missed out this one flood dam gate present here. So really getting them involved is pretty important. And in the post-disaster impact analysis, we need to understand that also our models are probabilistic. So there might be some discrepancies in the ultimate results of a model. But if we're able to collect the information about where our models are inaccurate or to what degree is that inaccuracy, we can update sort of our models not just for that particular location, but also for locations around which have similar features around in that particular event. And that is just about getting human insight and expert insight while you're developing your models. Now, there are also real-time observations. So for us in particular, they are river gauges, tidal gauges, seismographs, things on the ground which are measuring different parts of this impact. And what we try to do is while we're predicting this impact analysis, how do we leverage that input directly into our models? And how do we, during the event, auto-calibrate and use interesting data assimilation techniques. But post-deployment, how do we auto-tune our models? So it's important to get on-the-ground information as well as expert understanding in this complex problem of a disaster impact analysis. Now, data is the underlying issue for all sort of machine learning or physical models. And specifically for disasters, the damage data is very, very scarce. So the output label of your algorithms, there's mostly low damage events and a high, and a very, very small amount of high damage events. So it's highly possible that your algorithms are skewed towards low damage. And the second part is even the input data. So data about buildings, data about natural environment, lot of gaps, sometimes the data is not even present. Those two issues fundamentally sometimes cause us to not even think about how do we solve this problem. So what we try to do is we try to do 3 different ways. And number one is, can we learn from other geographies? So in California, where we first started, California hasn't seen any earthquake beyond 7 magnitude for the past few decades. So if we train an algorithm on that, and there is a high likelihood that there is going to be an earthquake beyond a 7 magnitude, how do we know that algorithm works? So looking at transfer learning techniques, looking at earthquakes in Japan or in different locations, and understanding the difference between the feature distribution in US versus Japan, and transferring those learnings is important. And this is a way in which we try to reduce the lack of data in just damage data itself. Now, the other thing we look at is, even if we get all the damage events across the world, there's still a lot of gaps in the damage output. You might have no damage about how steel buildings work with this particular soil type in this particular location. So when you don't have the damage output, how are you going to train your algorithms? So now we look at existing current state-of-the-art techniques. So you have physical models obviously existing which predict impact. So using those physical models and creating synthetic output data to fill in those gaps is another way in which we try to ensure that we have a complete understanding of the different type of damage impact analysis, damage impacts. And now looking at the input data, if you don't, for a long time when you're trying to solve these problems, people talk about if you don't have the data, your model is going to be highly inaccurate. I would instead say that why don't we look at creating, instead of focusing on deterministic data sets and probabilistic models, why don't we focus on probabilistic data sets and probabilistic models, and then exposing this uncertainty to our customers, right? Think creatively about how do we get these data sets. Think creatively how we use AI in the generation of the data itself. And that's another thing we also focus on so as to solve this issue around data scarcity. Now, given all these different data inference techniques, what becomes another challenge is risk and uncertainty communication, right? And you need to balance between, do we just don't do any solution? Do we just don't build anything because there's this uncertainty involved? Or do we just instead focus on explaining this uncertainty to your users, to the people who are actually on the ground, so that this can support them in their decisions? Or do we not innovate in this space at all, right? That's sort of the 2 things we have to sort of balance against. So risk communication is a whole entire industry. Everybody understands that it's an open research problem. And I'd love to understand how every one of you in this room is trying to make that better, especially when you're trying to work with naive customers or customers who don't understand these concepts. But we work a lot into ensuring that when somebody is using our decision support tool, they understand how these models performed in historical events, how uncertainties in the data transfer into the uncertainties in the model, and where we are collecting these different data sets and how a model is performing. So that when an actual event happens, when there's a stressful situation, these different organizations know how to actually react. Now, I've just been focusing on artificial intelligence techniques and physical models, but generally it's not always about the technological solution if you want to make it applicative. In fact, it's surprising that if failures and applicability go beyond the algorithm viability itself. For example, engineering. How important is engineering to convert a proof of concept into an actual application? Sometimes it's not even about creating models, it's just about getting the right computation power, the right data processing pipelines, so that you can actually predict at that scale. Now, if we were able to only predict one building and it took like 8 hours to predict the disaster that's already happened, that is not useful at all to the end customer, right? So we had to think about system architecture ground up as well in order to make sure that this is applicative in the first place. Other sort of non-AI techniques we look at is just network analysis. So I talked about the fact that we predict not just on buildings, we predict on water pipes, power lines, bridges, so that we can do holistic impact analysis. So we look at network analysis and graph theory on top of our AI algorithms to make what we have more useful to the use case which our clients are looking at. Now, I'll go through a brief use case one thing, so this is our example in Seattle. At Seattle, we have an earthquake product deployed. And first, we started with obviously the data set. So looking at multiple different types of data, public information, private information, information directly provided by Seattle. Seattle provided us actually information about the latest soft-story buildings, as well as provided information about the electric grids and the water pipes, right? So coupling all of those different data techniques together and inferring wherever needed when there were gaps. So we had a huge exercise talking to Seattle about where the uncertainties lie. The second thing was about the metrics we used with Seattle. Now, because this was a mitigation use case, wherein they actually wanted to understand which building should they strengthen, they didn't care about just one damage criteria. They wanted an average, they wanted to be, it to be accurate across all the different types of damage impact analysis. So both low impact, medium, and high impact. After we collected sort of the data, the metrics, and built the model around it, it was important to get them to understand the uncertainty behind it and how we validate it with recent events. And the recency of events is very, very important because, as we all know, these models are unable, physical models are more and more becoming inaccurate when you look at the latest, like very high extreme events. So we looked at all recent events in California, in Seattle, in Napa, and we showed case to our end customers, who are the city planners, where we would have gotten right and where we wouldn't have gotten it right. And ultimately, although, like I said, we created an impact model, ultimately it was built for building a use case. And the use case which the emergency city planners were looking at was, can you run multiple different scenarios? Can you tell me what is underlying damage impact? And can you change the underlying building data you have? And then tell me again, what's the impact going to look like? And can you do it multiple times so I can actually see which building should I focus on to retrofit? And that is sort of the example we have here, which was without retrofitting and without strengthening for the soft-story buildings, what are the different five risk criteria? And with retrofitting, which of them are still damaged and which of them are not? Now, so this is about direct impact, but something we're working on is about indirect impact analysis. Now, let's focus on power, and particularly for Seattle. So when we are talking about power impact, there's three stages we look at. Number one is, do they have the power data already, or do we need to even create a synthetic network around it? The second one is, how do you predict damage to the power, the power grid? And third one is, like, once we understand that part, how do we then predict the loss of power to every sort of home or every sort of commercial entity? So there are three actual models, and outputs of each ultimately result in the final deliverable. And as you can imagine, so Seattle, like I said, they provided us the power impact data, but we were able to at least validate our synthetic network generation with that power impact data, so that now when we have this use case, if we go to other cities, we can show them what the difference is. The second part, which is the power damage data, we just looked at different, the previous, the Nicole earthquake and what the damage was. And we sort of try to compare what is the difference between, and this damage report on the right-hand side is actually built only through synthetic data. We didn't use the actual data. We predicted what the power impact is going to look like with the assumption of the synthetic data. So we can explain to them that, hey, the uncertainties in the not having the data itself, how do they propagate into the power damage impact? But Seattle, obviously, if we actually had to, when we will deploy, we will use the real data they have. This is just to show how it would look like for cities when they don't have this information. And finally, the third one is prediction of power loss itself. That's more complicated to do. Right now, we're just using infrastructure constraints on predicting power loss. But it is important to actually have commercial entities and citizens be part and parcel of this process. Look at how the recent power disruptions look like, and tune your recovery models, not by using theoretical models, but by using what they're seeing on a day-to-day basis. So that's the third area of research we are focusing on right now. How do you use theoretical recovery functions, and how do you tune them based off of non-disaster power disruption event? Ultimately, we are focusing on a lot of other dependencies, power, water, structural integrity, transportation. The goal is that we want people to just understand what is the disaster impact during an event, and if you collate all the different scenarios in your city, what would that risk look like? We at One Concern, we're trying to build resilience as a service solutions. And we really believe that that's only possible if you look at artificial intelligence techniques as well as non-traditional techniques, supplementing physical model knowledge wherever needed, using compute to run these models quickly wherever needed, and using network analysis in places wherein you want to provide more holistic resilience understanding. Now, since we're in Switzerland, I just want to end with we aim to be the Switzerland of resilience. The goal is to get different stakeholders with different use cases, understanding why they should care about resilience. And I'm helping create a conversation among them so that they can just understand that, okay, this is the risk we all face. These are the different ways which we individually will work towards reducing or transferring this risk. And it's not just about the model, it really is about how they ultimately use it on the ground. So it's a broad spectrum. I think that's pretty much what I wanted to talk about. I'm looking forward to discuss this even more. These are a few of the challenges we faced when we are bringing this to different stakeholders. And I am glad that Swiss Re brought me here. So I'm looking forward to talk more. Thank you.